Hello, so if you've ever looked up at the sky, which I'm sure all of you have, you've probably seen the sun or at least glanced at it. But have you ever wondered what really actually happens within the sun? And how does it actually create all of its energy that we all take for granted? The sun provides energy for basically everything on Earth, including the water cycle, biological organisms, and things otherwise that we may not even consider. So how did the sun actually form? What is the sun really like in terms of its structure? And how does the sun actually go about producing its energy? So today I'll try to be answering those questions, and I'll start off with some basic statistics of the sun. So the sun is a pretty average size star. It's a spectral class G star, which basically means that it emits most of its light in the yellowish greenish part of the spectrum. As a result, the sun is brightest in visible light, which we can honestly tell quite easily because of how bright it is. Apart from the sun's specific spectral class, its spectral class is determined by its temperature, which is about 5,777 Kelvin. And as if you were to think about it in terms of a physics standpoint, objects that are really hot emit different wavelengths of light, and the hotter the object is, the shorter the wavelengths of light they emit. So for an object around a temperature of 5,700 Kelvin, the object will mostly emit yellow and greenish light, which is what the sun is. The light we see from the sun is not actually directly from the nuclear fusion. The nuclear fusion happens within the core, which is mostly confined in about a quarter of the sun's diameter. So most of the sun that we see is just glowing like a light bulb, essentially, because of the heat of fusion. Most of the sun's mass is concentrated, 90% of the sun's mass is concentrated within a quarter of its radius. As a result, most of the stuff that we see of the sun is actually, it's really light, it's not really dense at all. Apart from the general things about the sun that we know, like the sun's size, its temperature, and its mass, the sun also varies in the time aspect as well, and it's measurable in a human lifetime. Every 11 years or so is called a solar cycle. And basically what happens in a solar cycle is that the magnetic field of the sun sort of flips direction. It changes polarity. This is not something that we see on Earth, although it has happened in Earth's history as well. But it has to do something with the magnetic field getting twisted in the sun's rotation, and over 11 years it reverses itself basically. And if this cycle goes, if there's something wrong with this cycle, or if the cycle doesn't go as planned, the sun's luminosity, or how bright the sun is, can actually decrease slightly. And this is actually what happened in something known as the Little Ice Age, which basically occurred between 1615 and 1715. And it's basically where the solar cycle ceased to exist, and the sun didn't really experience any significant magnetic field activity. So the solar cycle is really important. Before I talk about how fusion works, I'm going to show you what the sun's layers are actually made of. So the outermost layer of the sun is called the corona, and it basically encompasses everything that's beyond our spherical star that we call the sun. And this is basically where all the solar wind of the sun is produced. And some other interesting facts about the corona is that it's much hotter than the actual surface of the sun, but because it's consisting of very few particles, the density of the matter in the corona is very low. It doesn't really physically get that hot if you were to actually be there. So you could send a spacecraft there and it wouldn't get hot because of the corona. It would mainly get hot because of the actual sun's light. So going past the corona, the second layer of the sun, if you go downwards, is called the chromosphere. And this is basically a thin layer around the sun's main layer, which is the photosphere. And this is where interesting things like solar flares and prominences occur. And these are particularly important because solar flares, they can cause geomagnetic storms, which can disturb electromagnetic activities on Earth, such as power grids and wireless communications. And but other than that, that's basically what's really important about the chromosphere. Then going on to the photosphere, this is what we call or see as the sun. It's basically a bunch of glowing hydrogen and helium. Those are the two main components of the photosphere, with hydrogen being about 74% and helium being around 23%, and plus some other elements. And this basically glows like a light bulb, as I explained to you earlier, which is where we get most of the light of the sun. So because the photosphere glows because of the heat coming below the surface, the heat that we actually receive from the sun was actually formed a really long time ago. Estimates say it takes around between 10,000 and 100,000 years for light from the core of the sun to reach the surface. Okay, so after the photosphere, we go on to the convective zone, and this basically extends to around 25% of the radius below the photosphere. So basically everything between like the outside of the sun and a quarter of the way into the sun, that's the convective zone. And so basically in the convective zone, heat is transferred from within the radiative zone, which transfers heat from the core in the form of radiation, and the material beneath the core, between the core and the convective zone, just sort of bounce and absorb and re-emit photons until eventually it reaches the convective zone. And the convective zone, if you think about boiling water, right? Boiling water, when you heat it up, it convects. The fluid transfers heat from your heat source to the top of your water, and it cycles around. And that's basically the same thing that happens in the convective zone of the sun. That's basically how the heat transfers from the interior of the sun to the exterior, and how we see it as light. Now moving on to the radiative zone, and this was, as I mentioned before, it's basically a region of the sun where radiation escapes from the sun's core and travels to the convective zone. And temperatures in the radiative zone can climb up to 7 million Kelvin towards the sun's interior. And then we reach the sun's core, which is obviously where all the nuclear reactions take place, which actually power the sun. So the nuclear reactions of the sun happen at a really astonishing rate, at a rate of 600 million tons of hydrogen being fused every second. Every second of the sun's life, basically, for the past 4.5 billion years, the sun has been fusing hydrogen at this rate. And because of the way nuclear fusion works, about 4 million tons of that mass is converted to pure energy, and that's the energy that the sun emits as light. So how does exactly fusion work in the sun, and what is the exact process that happens? So the thing is that fusion in the sun, there's many different ways that you can fuse elements in a star, but the sun, because of its low mass, relies mostly on the proton-proton chain. This basically, what happens in the proton-proton chain is that you take two protons, or two hydrogen nuclei, and they collide together at such a high velocity that one of them turns into a neutron. And when this occurs, you get a nucleus of deuterium, which is just heavy hydrogen. You then need additional protons to collide into the deuterium to eventually create helium-3, and then helium-4, which is the main product that the sun creates. And all the tiny amounts of energy that is lost when a proton converts into a neutron, that energy is what actually comes out to us as light. There's also something known as the carbon-nitrogen-oxygen cycle, which is a way that stars of a slightly higher mass than the sun fuse, and then even higher mass than that stars fusing using the triple alpha process. This basically consists of combining 3 helium nuclei together and carbon nuclei, which is basically what's going to happen with the sun later on in its life. So how did the sun actually get here in the first place? Well, the sun began its life about 4.5 billion years ago, and back then the solar system was just a giant molecular cloud, which is a big cloud of hydrogen and helium gas mostly. Essentially what happened was that something caused the molecular cloud to collapse and shrink, basically. It might have been a supernova event, it might have been the molecular cloud crashing into another molecular cloud. We don't really know exactly because it was so long ago. But something caused this molecular cloud to contract, and that's basically resulted in the creation of the solar system. As the molecular cloud contracted, most of the mass, in fact 99% of the solar system's mass, came into the center and started forming the sun. And since then, eventually nuclear reactions started in the sun's core, and here we are today, 4.5 billion years later, with the sun still going on, and Earth having the diversity of life that it does. But what will exactly happen later on in the sun's life? Well, 4.5 billion years from now, approximately, the sun will have run out of hydrogen to fuse, and it will begin fusing helium. However, once it does that, it will enter the red giant phase of its life, which is right after the main sequence. In the red giant phase, the sun will expand to the point that it will probably consume Earth, and so the Earth will eventually become a part of the sun. And it will go through several cycles, several pulsation cycles, that will cause the sun to shed about half of its mass. Once it does that, the sun will turn into a white dwarf, and eventually, after trillions and trillions of years later, the white dwarf will cool, and it will turn into a black dwarf, and that will basically be the end of our solar system. But if there's one thing I want you to take away from this video, it's this: the sun is amazing. There's really nothing that we can actually do as humans to compare to the sun. And if the sun didn't exist, we wouldn't exist. It's really that simple. So the next time you go out, take a walk, enjoy the sunlight, enjoy nature, because honestly, without the sun, neither of that nor yourself would exist. I hope you learned something, and if you really enjoyed what I taught you, then I would encourage you to subscribe or check out my other videos. I want to make more videos explaining science content in the future with hopefully a better quality. Obviously, I'm just getting started, but yeah, and I see you soon.